Hey everybody, I am here to continue the tutorial and show you a different way to calculate cross-sectional area and discharge using these velocity measurements. So this is a different cross-section that we took by measuring distance and water depth, and I'll use it to calculate discharge here. So first I'm going to spiff this up a little bit and just add some points for myself. This will help us visually when we plot the cross section. So I'm just going to add the left edge water and the right edge water so that when I plot this, it'll look nice and we can have a horizontal water surface. So our edge water here, it was at 10.2. And then the right edge water was at 24.4 on the tape. We use the same tape to measure these two, so we can do that. The water depth of both of these, since it was the very edge, was 0. Okay, and now we have two bounding points of the cross section. Now let's just add a, nope, don't want that. It might be right, but let's add this velocity cross section. X is going to be distance, which I blocked out by doing that. So I'm going to change that to L. And then Y will be the water depth. Okay, so we have a cross section here. It's just upside down. And for now, I'm just wanting to look at this visually. And so I'm going to just, first I'll move it down. I'm just going to reverse this axis. Values in reverse there. Okay, so now we have a cross section. I'm going to add one more series actually for the water surface, which is going to be at 0. But I'm just going to select those first and last points. I always put this right in front of where I want to go. Okay, so now we have a water surface. That's our velocity cross section. Okay, so each of these points of distance is representative of an average depth between two other points. So the width between all of these measurements that we took is 1.4. So that's going to be the width of each rectangle. And then this velocity that we measured is the average velocity per rectangle, and the depth represents the average depth per rectangle. So we can actually visualize this differently than what's in this. See how the rectangles go from point to point, but the water surface is not included in here. This is why it's a different way of looking at it. Now we're looking at the water surface marks as our bounding points. So each of these 10 points actually represents the average depth and velocity of a rectangle in the channel. So we're going to use them as is. They're in centimeters right now, so I want them in depth, the depth in meters. First thing, so I'll just do that divided by 100. That way we can get cubic meters per second for our discharge. Okay, since we're doing it the easy way, all we have to do now is the width times the depth times the velocity, which is the equation for discharge. And remember I said each one of these is 1.4 meters apart. So our width will be constant at 1.4 meters. And we did that because the top wetted width here, total, is going to be the right edge water minus the left edge water. So our top wetted width of what we measured in the field that day, all the water was 14.2 meters wide. And so when we divided it into 10, we divided it into 10 equal sections that were 1.4 meters apart, which is 1/10 of this top wetted width. So just to prove that to ourselves, the width of each one of these rectangles, starting with the points that were originally in the cross section, is 1.4. And so you'll see that's going to be the same for all of these. Oops, except for that one, because that's with the point I added, so I'm going to delete that. Okay, so our width will always be 1.4. So now we want discharge, which is width times depth times velocity. We'll just call it WdV. I'm just going to do for the points that I measured here. So our 1.4, or I could choose that column next to me, times depth in meters times our velocity. Okay. Cool. So now if we add those all up, that's going to be our total discharge. And it's okay if you did it the other way and you only had 9 rectangles. It might be a little different, but as long as you're close. The reason why they are different is because we measured this cross-section specifically by dividing it into 10 sections and measuring velocity. If you were doing this in a real-life scenario and you had a bunch of velocity measurements, you would do it like the other videos that I showed you, where you would have one less number of rectangles as you did the number of points. Okay, so our total Q there is 1.68 cubic meters per second. So when I looked it up, which I don't see it, I thought I pasted it in here, maybe not. I looked it up on here, 60.3 cubic feet per second. I don't have my conversion factor memorized or pasted anywhere, so I'm just gonna do this real quick. Thank you, Google. I don't want that. So just gonna do this 60.3 for, excuse my laziness here. And then that's gonna be what I'm comparing it to. Okay, cool. So that's actually really close. Very nice. So it's a little different. That could be for a few reasons. Maybe the gauge where this is measured is a little bit farther downstream and there's a little tributary coming in, which is especially possible during the spring where you've got a lot of snow melt. Or maybe the way that we measured it is oversimplified because we only divided the channel into 10 points. So there are a couple reasons why it could be different. You can use your brain and be creative about that.